Good day all. We are presenting our project as we have proposed initially that we are working on EEG movement correlation. And with me, I have Novin Sadni. I also have Lukmo and Garatilin. And my own name is Rahman. Now, the area of application of this project, as we've collected the data set, is we tabulated from electroencephalography scan of patients performing the elementary task of moving one's arms or speaking. This data endeavor us, we categorize the data as one with healthcare improvement aims through general medical and state attribute inference. The objective of our project, the first one is to develop a scalable data analysis pipeline. The second is to optimize performance, storage, and resource utilization. While the third is to enable efficient decision-making and insight extraction in a big data environment. The last is to filter redundant attribute through pipeline.
For our problem statement, we predicted that there will be a delineable difference between attributes related to different actions. And the hypothesis which we tested is that there will be differences in our attributes, which will make some attributes more useful to our prediction than others. And the brain activity will have distinct patterns that will allow us to classify it into multiple groups. For the specifics of our data, we have 96 continuous values with one classification value. And our EEG readings are very small. They read very many times a second with a lot of attributes. So we needed to do a lot of scaling, checking for null values and checking for the relevance of variables. And we also conducted correlation analysis to determine which of our signals should be used and which ones to ignore. So this right here, this screenshot shows a breakdown of our classifications, both before and after applying SMOTE. And SMOTE is a process of balancing out our output classifications through synthetic sampling. I might have one more actually.
Okay, so one thing we did to remove multicollinearity between our attributes was apply an upper bound via variance inflation testing. This upper bound at first was less than 6, so our minimum value was approximately 5 point something. So we got about 5 attributes between 5 and 6, but we're performing poorly on our testing. The reason for this is because we reduced our dimensions too far. So we increased the upper bound to about 10 and got better results. So for the significance, we discovered and defined relationships between our attributes provided by the electroencephalography scans in such a way as to be meaningful and repeatable. And given the large volume of data, pre-processing and computationally efficient algorithms were demanded to do this in a short amount of time. So this is an example of the distributions of our attributes. Here they have been normalized and plotted in histograms via a specific amount of buckets, and they are graphed on top of each other so that you can see the variance in distribution between some of the attributes.
All right, so now going into our different modeling methods, we begin with random forest, which on our training accuracy received a 100%, and on testing accuracy received almost a 96%. For the SVMs, like the random forest, training accuracy was at 100, and the testing accuracy was at 97.85%. Rarely misclassifying any motions. And the quadratic discriminator also came out with the 100% on the training and gave us our best testing result yet of 98.85%, only misclassifying less than 10 signals. So in conclusion, the quadratic discriminator was the most successful classifier, and SMOTE, VIF, and collinearity testing were very important when turning our EEG dataset into meaningful predictions.
Thank you for listening.